Welcome to the AI Research Roundup. I am your host, Alex. Today is May 12, 2025. We're looking at an ICLR conference paper, WizardMath, Empowering Mathematical Reasoning for Large Language Models via Reinforced Evol-Instruct, published just a few months back on January 22nd. This paper tackles how many LLMs, especially open source ones, struggle with complex math. It introduces WizardMath, a model to enhance their mathematical chain of thought reasoning. That's their ability to think step by step, without external tools. The core method is reinforcement learning from Evol-Instruct Feedback, or RLEIF, which trains the model using specially evolved math instructions and feedback on its reasoning. Okay, so this figure 1, visually breaks down their reinforcement learning from Evol-Instruct Feedback method, which is key to their results. It's a 3-step pipeline. First, Math Evol-Instruct generates diverse math problems, then used for supervised fine-tuning, a process where the model learns from correct examples. Second, they train 2 crucial reward models, an instruction reward model, assessing problem quality, and a process-supervised reward model, checking each reasoning step. Finally, the main LLM is optimized using proximal policy optimization, an algorithm using feedback from both reward models to significantly enhance its mathematical problem solving. Alright, so building on that reinforcement learning from Evol-Instruct Feedback method, this table 1, really shows the impact. It lays out the model's chain of thought pass at 1 results. That's the percentage of problems solved correctly on the very first attempt on 2 standard math test sets, GSM 8K and Math. We see WizardMath models, for instance, WizardMath Mistral 7B and the larger WizardMath Llama 70B, significantly outperforming other open source models and even some well-known proprietary ones. This performance really underscores how effective their approach, using the instruction reward model and process supervised reward model with proximal policy optimization, actually is. Okay, so this next plot really drives home the point about data efficiency. We're looking at how the accuracy of the Mistral 7B model changes on both the GSM 8K and Math benchmarks as the amount of training data increases. The solid lines, representing their WizardMath approach, consistently stay above the dashed lines for another model, MetaMath. This clearly shows WizardMath achieves higher accuracy using less data, which really highlights how effective their Math Evol-Instruct method is for generating quality training examples. It's a strong visual for better learning with fewer resources. Okay, so building on that data efficiency we just saw, this table 3, really zooms in on the specific contributions of their specialized reward models during the proximal policy optimization training. It shows different base models, starting with just supervised fine-tuning. Then, the authors add the process-supervised reward model, which, as we discussed, evaluates each step in the model's reasoning, and the scores improve. When they also include the instruction reward model, which assesses the actual quality of the math problems, performance on both GSM, 8K, and Math jumps again, often by a good 6 to 8%. This really highlights how crucial both these reward models are. So, to really see these reward models in action, Table 9 gives us a specific case study. It's a math problem from the GSM 8K test set, and we see the model's step-by-step reasoning. Alongside each step is its process-supervised reward model score, and there's also an ORM score, which appears to be an outcome reward model evaluating the final answer. The red text highlights where the reasoning went wrong, and notice how the process-supervised reward model scores drop sharply for those incorrect steps. This really shows its fine-grained error detection, something the outcome reward model, with its relatively high score for the wrong final answer, didn't catch as effectively here. Alright, so after seeing how the process-supervised reward model pinpoints errors, let's look at how the training problems themselves are actually generated. This figure, example 4 from page 21, shows their Math Evol-Instruct process in action. For each original instruction, we see a corresponding Evol instruction. Notice how these evolved versions are often more detailed, sometimes adding new constraints or explicitly asking for specific solution methods. This is a great illustration of that upward evolution they mentioned, essentially making problems more complex or guiding the reasoning more thoroughly, which is key to creating richer, more diverse training data for the LLM. So after seeing how Math Evol-Instruct creates those richer problems, It's clear how all these pieces contribute to the overall success. The main takeaway here is that WizardMath, through its novel approach called reinforcement learning from Evol-Instruct Feedback, or RLEIF, which is a method that refines the model using feedback on both the problem's quality and the solution's step-by-step accuracy, really boosts the math reasoning of LLMs. This strategy, combining the specialized reward models we've discussed, leads to impressive performance, even surpassing some major proprietary models. Thanks for tuning in to the AI Research Roundup, and we'll catch you next time.